time to learn about the integral test. Now, in many of the videos I make, before I tell you what the main idea is, I try to show you some examples first to get you thinking about things the right way. That's at least what I try to do. With the integral test, I think it's best if I just tell you what it is and show you the examples. Perhaps after I finish this video and I get it posted and you start working on the quiz, I'll make another video about why the integral test works. But for now, I think it's best if I just tell you what it is. So you have an infinite series, and that a subscript n, that's just our generic symbol for the formula that's going to be there, that's going to involve the variable n. And say I call that f of n, a formula or a function that involves n. Okay? All right, now suppose that we convert over and we use x as a variable in an integration, all right? And suppose that that function, which is really just this one with x instead of n, is positive, decreasing, and continuous for x greater than or equal to 1, okay? All right, so that's all like the setup and the fine print for the integral test. Here's what it tells us. We use the integral test to figure out if a series converges or not, okay? That's our big question that we're dealing with right now in Calculus 2, is you have a series and we want to figure out, does it converge or does it diverge, all right? So with the integral test, here it goes. You set up this improper integral from 1 to infinity. If that integral converges, then the series converges, okay? What does it mean for an improper integral, like an integral from 1 to infinity, to converge? If the value of this integral is a finite number, if it's a number, okay? So the integral and the series do the same thing. They both converge. Case 2 is, say you set up this improper integral and you work it and it gives you infinity, meaning the integral diverges. Well, that means the series diverges. So you can think of it that the integral and the series do the same thing, okay? Now, we learned about improper integrals in, well, so I don't know. I think it was one of the first videos I made after we had our last test, but you could go back and look up a little bit about that if you need to, okay? But it's something that we've talked about. Both of these integrals, because of that upper bound being infinity, are improper integrals. So, all right, let's try this and see if we can get it to work. So here's the first series I give you. Decide if the series converges. So let's use the integral test like this. Okay. The integral test says we're going to evaluate this integral from 1 to infinity. Okay, just like the series is from 1 to infinity, we'll find this integral from 1 to infinity of 1 over x to the 4th power dx. Okay, so that's what we're setting out to do. We're going to figure out the answer to that. The way that we had done these improper integrals is actually like this. You know, infinity is not a number that we can do calculations with. So when we want to evaluate an integral that involves an infinity, we put a number b there, which we control and push to infinity. We can't actually have infinity, but we can push towards it, all right? So that's the proper setup for that kind of integral. All right, now the antiderivative of this is going to be negative 1 over 3x to the 3rd power, okay? And that's going to be from 1 to b, and I need to let b go to infinity. All right, whoops. Okay, so that's where we are now. So at this point, here's what I'm going to say, since we've done lots of integrals. If we put b in there, all right, it's going to look like this. This is the most we can say about it. 1 over 3b to the 3rd power. That's just what it is. But we're going to push the b to infinity. And then that lower bound is going to give me a 1. I'll just put like that. Okay, so now what happens? B goes to infinity. What happens to 1 over 3b to the third power? Well, if b goes to infinity, b to the third power is going to get very, very big. And the larger number you divide by, the smaller and closer to 0 this is going to be. So this is going to be equal to 0 minus negative, so plus 1/3. Okay, so the value of my integral is 1/3. It's not infinity, okay? The integral converges. All right, so what do we say about the series? The series converges too. Okay, all right. The integral converges. I get 1/3. I get a finite number. It's not infinity. That means the series also converges. Okay, now it's black and white. It's cut and dry to use the integral test. So long as you know how to work an improper integral and deal with the infinity and the limit and so on, okay? I need, though, to tell you some additional details about it, okay? So here's what we just figured out. We did this integral and we got 1/3. I'm not saying that that series converges to 1/3. What does it mean if that series converged to 1/3? That would mean the more terms of this you add together, the closer your grand total is to 1/3. That's not what the integral test says, okay? The fact that this integral was finite only proves that the series converges to something. We're not saying that the series converges to 1/3, all right? What does this series converge to? Okay, if it converges, it's got to converge to something. And what I mean by that is if this series converges, then the more terms you add, the closer your grand total gets to some number, all right? It's just, it's not 1/3 though. So what I did is I made a little chart of the partial sums. Here's your series from 1 to infinity, 1 over into the 4th power. It's 1 plus 1/16 plus 1 over 81, and it keeps going. If you add the first 2 terms, you get 1.06. The first 3 terms, 1.07. If you add the first 4 terms, 1.08. From there, the grand total really seems to level off. You know, adding the first 4 terms, you're at 1.08. Adding the first 7 terms, you're at 1.082, all right? So this series converges not to 1/3. It converges to something more like 1.08. I can't, you know, making a table like this and calculating partial sum, it doesn't tell you exactly what the series converges to. But it would be safe to say that it's something that's approximately 1.08, okay? So the series converges by way of the integral test. We estimate it converges to about 1.08, all right? Okay, let's try another one. Let's try this one, okay? So if we're here at this point, and we use the integral test, then that will involve doing this integral. 1 to infinity, 2 n, and oh, let's use x. I'm sorry. I guess it's not the end of the world if you used n as your variable of integration, but it's a little more agreeable to people to use x. Okay, so 1 to infinity, 2x over x squared plus 1. Now, this integral here is of the form 1 over u du, okay? That's what kind of integral it is. So if you do that and replace this infinity here with b, it'll be like this. The limit as b goes to infinity. The antiderivative will be natural log x squared plus 1. And then we want to do 1 to b. All right? Okay, so you'll get that antiderivative through a simple u substitution. It'll be 1 over u du. If you let x squared plus 1 be u, then the du is 2x dx. It's all right there. That's your antiderivative. We replace the infinity with the b, and we'll push the b to infinity. And then that's going to look like this. What's the limit as b goes to infinity of natural log b squared plus 1 minus what turns out to be natural log of 2. Okay, I put in that upper bound, it looks like so. I subtract, I put in that lower bound of 1, and I get natural log of 2. So, all right, so we're here. What happens when b goes to infinity? B squared also goes to infinity. B squared plus 1 goes to infinity. What's natural log of a number that's just getting bigger and bigger and bigger out to infinity? Well, for a logarithm, the bigger number you take the logarithm of, the bigger the logarithm itself is. So this will go to infinity also. All right. So our result here is infinity minus natural log of 2. And natural log of 2 is a finite number, a constant, so that's just infinity. All right, so this integral diverges. Okay? All right. That means what? That means that this series diverges. Okay? That means this series is not such that the more terms you add together, the closer your grand total gets to some specific number. All right, that's what it means when we say it diverges. I when I was putting all this together, I used Excel and I calculated some partial sums. Okay, so for this series right here, the sum of the first 10 terms is about 4.5. Okay, the sum of the first 50 terms is about 7.6. And then the sum of the first 100 terms of this series right here turns out to be about 9.03. So does that seem to confirm, or does that seem consistent with the fact that we proved it diverges? The integral test proves definitively that that series right there diverges. And I'm not surprised then that when I take this series, the more terms I add together, it's just the bigger the grand total is. It doesn't seem to be leveling off. It doesn't seem like the more terms I add, the closer my answer is getting to something, all right? So, yeah, here's the partial sums. And it's just like my commentary, and something that I think that you should be able to realize about this too. That it definitely seems to diverge. Now the partial sums, they don't prove anything. The integral test proves that the series diverges, but I'm just not surprised about that's the way the partial sums work out, given that it's a matter of fact that that series diverges. Okay, so I wanted to give you the series. I wanted to work through the integral test, prove that it diverges by way of that, and then show you some of the partial sums to see, yeah, it looks like the more terms you add, it's just the bigger your answer is. The more terms you add, it doesn't seem to approach anything. Okay? All right. Let's do one more, start to finish problem. Okay, so this one here. So how about this? Let's use the integral test like we did for the others. That's what we're practicing at this point. So the integral test is the integral from 1 to infinity, 2 to the minus 2x dx. Okay? All right. So let's see. This right here is of the form, there's this form of integration, a to the u du, whose antiderivative is a to the u power over natural log of a plus c. So that's what kind of form that we're going to be dealing with this one. U is going to be negative 2x, all right? And du is going to be negative 2 dx. Okay, so that's how it works. That's the form of integration that it actually is. And what you'll get is this. Because we've done lots of integrals, I'm just going to tell you the antiderivative that you'll get based on this substitution right here. So you'll get negative 1 over 2 natural log of 2 times 2 to the 2x power. Okay? And that can be consolidated quite a bit if I needed to. But I'll go ahead and leave it. It will work for our purposes. Okay? All right, so that's what I've got. Now, let's continue over here. I've got my antiderivative right there from u substitution. And now putting my bounds in, on the b first, I get negative 1 over 2 natural log 2 to the 2b. Okay, putting b in for x. Then I'll be subtracting what turns out to be a negative. And when I put 1 in, I'll get 1 over, okay, so what's that going to be? 2 squared, that's 4. So I'll get 8 natural log of 2. Okay. Whoops. Okay, I didn't realize that was off screen. So anyway, I have my antiderivative. I substituted the bounds. Now take a look at this right here. What happens to that as b goes to infinity? So b goes to infinity right there. You see that exponent? And 2 times b is going to go to infinity. And 2 to that power, I mean, imagine taking the number 2 and raising it to powers that are getting bigger and bigger and bigger out to infinity. This entire denominator here is going to go to infinity. And 1 over that will go to 0. Because the larger number you divide by, which is what's going to happen down there, the smaller and closer to 0 your answer is. So here's my result. It's 0 plus 1 over 8 natural log of 2, or just 1 over 8 natural log of 2. And that's not infinity, okay? So what did the integral test prove for us? We did this improper integral. We got, I really don't know what that number is. I don't know what 1 over 8 natural log of 2 is without a calculator. I could maybe roughly estimate it, but I don't know very closely what it is. But I know that it's not infinity. So this integral converges. We say an improper integral converges if its result is a finite number. So the integral converges. That means that the series converges also. Okay. All right. Does this series converge to that number? No, that's not what we're saying. This here, just being not infinity, only proves that the series converges. It doesn't tell us what it converges to, okay? Now, all right, so I wanted to show you this last example of the integral test. We've done lots of integrals, so I'm, unless you tell me, I might assume that you're okay with the substitutions that might be involved, the limits that might be involved. You can always ask for more help on that if you need to. But I'm curious if there's something else about this that you noticed, okay? So, did you notice anything else about that series? Well, so I had kind of a tunnel vision when I showed you this problem. I just wanted to practice the integral test. I just wanted to show you how that worked. But this also happens to be a geometric series. Now, once I get all the videos made, I'll make a summary video about everything. We have infinite series. We have geometric series. We have telescoping series. I just posted a video an hour ago about something called the nth term test, which allows you to prove that a series diverges. And now you got the integral test. So you got all this stuff. At some point, I'm going to make a summary video where you just see everything in one place. And hopefully that'll allow you to get the big picture. But this one, you may not have noticed it when we were doing it. It is also a geometric series. We could analyze it from here to here, right? Because when you take a number, raise it to a power, then another power, you multiply them. So I take it back apart. 2 to the minus 2 power is 1/4. All that series ever was 1/4 to the nth power, okay? All right. Now, so about that, it's geometric series. R is 1/4. That means it converges. If R is between -1 and 1 for a geometric series, it converges. It converges, in fact, to 1/3. So when we use the integral test, it only told us that it converged. It didn't tell us what it converged to. When I realized that it also happened to be a geometric series, I figure out it converges to a third, okay? What does that mean? It means the more terms of this series you add together, the closer your grand total is going to be to a third. Try it out. If you don't believe me, or if you think it would help you understand, I mean, when I'm doing math, I like to think about numbers. I like to think that numbers are actually involved. So I could get my calculator, or I could make an Excel spreadsheet, and I could start adding the terms of this together. I'll find that every time I add another number, the answer I get here is closer to what? A third, okay? All right. So one more thing, and I think we'll be done, at least with this video, for the integral test. There's some fine print about the integral test. Try to think about the very first slide that I showed you. Where was it? There's the first slide. And it says that you have a series, and this formula, this function that the series is based on, is positive, decreasing, and continuous for more than one, okay? So that is the fine print. So here's the first problem we did, okay? In order to use the integral test on this series or any other series, we need to prove that, this associated function is positive, decreasing, and continuous for x greater than or equal to 1. I didn't do that on every example, but really these three things have to be established in order to use the integral test, okay? I took it for granted on the problems that I showed you just to show you the integral test, but now I want to talk about those three things. Now, first of all, is it obvious that that is going to be positive if you put a number greater than or equal to 1 in? Sure, 1 over x to the 4th power will be a positive number if you put anything into it, especially something bigger than 1. Is it decreasing? Well, what's decreasing mean? It means the bigger x I put in, the smaller the y is. If x is bigger, y is smaller. That translates to the derivative being negative. So to show that this is decreasing, we would have to establish that the derivative is negative when the x is bigger than 1. And so here's your derivative. It's negative 4 over x to the 5th power. And that will be a negative number if you put x bigger than 1 in, okay? Sure, because why is that? You put something bigger than 1 in, you raise it to the 5th power. That's going to be a positive number. And then you take negative 4 and you divide by that number, it's negative, okay? So that's how you establish it's decreasing. In continuous, well, you can spot discontinuities in a function. Like this function here is actually not continuous. At 0, all right, because 0 is not in the domain. It has a vertical asymptote at 0, but we can see that it's continuous if x is greater than or equal to 1, all right? You're not going to have any problems there with continuity for x greater than or equal to 1. So yes, you would have to establish those three things. I drew a little graph of what 1 over x to the 4th power looks like from 1 to infinity. You can see every point on here, the y-coordinate's positive, is decreasing because the y-coordinates are getting smaller as the x-coordinates get bigger. That's what this established. And it's continuous. There's no breaks, holes in the graph, vertical asymptotes from 1 to infinity. Okay? So that's the fine print. Before you use the integral test, just verify those three things, and then you can use it as you saw in the video.